Hi everyone, welcome to Mostly Math. Today we will be evaluating this integral, which I found on the Math Facts Facebook group. Definitely check it out. It's a great place where a bunch of Indians get together and try and challenge each other to see if they can evaluate sums and integrals. So even if you're not Indian though, you can indeed learn many useful tips and tricks from them. This particular integral I know has a usage in physics in terms of electrodynamics. Or as we call it, E&M, if you actually take the physics course. I believe this has something to do with the dipole moments, but don't quote me on that. It's been a while since I took the course. But integrals like these are useful in real life. Excuse me. I'm going to evaluate this one using a few very simple tricks. I just wanted to take a short break from all the complicated videos about the tensor calculus that I posted recently, so I wanted to do something more elementary, ordinary high school level, or freshman college level stuff. So this integral can actually be solved by a simple u substitution, but before I get into that, we have the integral over all space with respect to a variable x of ax plus b, so a linear function over x squared plus 2r, so r is a constant, and so is lambda. 2r x cosine lambda plus r squared. And these are just constants, and you might ask why they're called this. There's some kind of a reason in physics that I forget. So let's proceed. The trick is to consider a clever u substitution, but before we can see what u is, we have to notice that the denominator can actually be written in the form of a completed square. So we want to consider the following quantity: x plus r cosine lambda squared. We might want to do this because we notice that the bottom looks like it could be this plus a constant, so we just want to find out what that constant is. And we might think that because we have three terms, these two squared, and there's a 2x term in there, so we think that it could be a square of something. So let's just evaluate this and see what we get, which is obviously x squared plus 2r x cosine lambda plus r squared cosine squared lambda. Well, this is not quite what we have on the bottom, but it's pretty close. So this tells us that what we have on the bottom can actually be written as what we were considering here, the square of this quantity, but with a few differences. So this term doesn't have an r squared, so we have to add one. And it also has an extra r squared cosine lambda term, so we have to subtract that. And notice the miraculous thing here, this quantity here is just actually sine squared lambda. So the quantity that we are looking at is simply the thing we had before, plus r squared sine squared lambda, which is pretty cool. It's definitely in the form of a completed square, and it's a special square. It's this squared plus the square of something else, which is really cool for reasons that we'll see in a bit. And now we want to write our integral in terms of this new substitution. We wrote it as integral from minus infinity to infinity dx ax plus b over the new thing, x plus r cosine theta r cos lambda squared plus our new term r squared sine squared lambda. Let me just make sure I'm getting all the correct terms here. Yeah, that looks pretty good. Okay, so now it's pretty obvious what we should use for our u substitution. Well, actually there are really two choices. You could let ax plus b be the substitution and see where that gets you, but it's not going to really get you very far. The second thing that you would consider was to let the new variable x plus r cosine lambda be the u substitution, since we have now written it in the form of, 1 over something squared plus a constant squared, basically, with some crap on top, which looks like it could potentially be an integral that we could do. So we certainly want to use the u substitution for a new variable here. So we're going to let our new variable x prime be x plus r cosine lambda, which of course immediately tells us that x is equal to x prime minus r cos lambda. And it also tells us that we have x prime with the same limits as x, since we're just subtracting or adding r cos lambda, which doesn't do anything to plus or minus infinity. And we also know that dx prime is equal to dx, since if we just take the differentials of this expression, this is just a constant, since it doesn't depend on x. Excuse me. Okay. Now we can write this integral in terms of our new variable. We've already solved for x, so we're going to plug that in there. Dx prime, I've just noted, is unchanged, and now we have a couple squares on the bottom, which is pretty cool. So this is an aside, and now we write our expression integral from minus infinity to infinity with respect to x prime. Now we have let's go ahead and do this for clarity. Why not? Woo! Just so it's really clear what I'm doing. Okay. We've already solved for x prime. We know, or rather x here. X is just x prime minus r cosine lambda. I don't know why I can't write these Greek letters today. And plus b, of course. And now we have x prime squared plus r squared sine squared lambda, which we want to factor out a few things. We know that there's a common dx prime and a common denominator. And we get a constant plus a linear term. So the linear term is just going to be ax prime plus the constant. We have this term minus ar cosine lambda, and then you add to it b. So we get just the constant here, b minus ar cosine lambda. And we see immediately that one of these integrals is 0. In fact, this integral is going to be 0 because it is an odd function. And I'm using the property that if we have the integral of an odd function over a symmetric domain, it's 0. Since, if we have the sine function, for example, sine function, this is 2 pi here, we have the positive area is going to be equal and opposite to the negative area. So when you add them, it's 0. That's basically what this says, and we can claim that this is 0 because if we let x go to minus x in this expression, if we had x over x squared plus a squared, well, c squared, we know this is an odd function because as x goes to minus x, we actually have minus x over x squared plus c squared, which is the same thing that we had before with the minus sign out front. So we can now conclude that it's an odd function and the integral over the symmetric domain is 0. Sorry if that's a bit more detail than you needed to evaluate the integral. This is just such a simple problem. I just wanted to be more clear since I have the time. Okay, odd function over symmetric domain. And we're left with a constant times this integral here. So it's just going to be b minus a r cosine lambda. I really hope that's right. Yeah, looks right. There's just so many constants. It's hard to keep track of them, you know. And we're going to evaluate this integral now. We're going to be using the fact that if we had the integral over all space of dx over x squared plus a squared, it's simply 1 over a inverse tan of x over a. Just an ordinary formula from freshman calculus. I'm sure you all recall it. So this is going to be our a, of course. It's just r sine lambda squared. So a is just r sine lambda. No problem here. And this is just equal to 1 over a. So the constant is now going to be divided by r sine lambda. We have an inverse tangent of x prime divided by our a. Sorry about the confusion with the a, but I think you can tell the difference between the a we had at the beginning and the a we have up here. This is, of course, evaluated at x prime is equal to infinity and x prime is equal to minus infinity. Notice all the variable dependencies will actually go away, since this is just going to be pi over 2 minus pi over 2, which equals pi, of course, since we're just taking arctangent of infinity. Arctangent graph, as you recall, looks something like this. Oh, that was so bad. Arctangent graph looks something like this. So we have plus pi over 2 here. And we have minus pi over 2 here. So when you look at the limits and subtract them, they just become pi, of course. And we pretty much have our final answer now. All we have to do is put a pi up here. B minus a r cosine lambda over what we had before, r sine lambda. And this is, of course, the value of the integral. And we are done. So congratulations, everyone. We have just evaluated this rather nasty looking integral with a linear function over a weird quadratic thing. In terms of number pi, we got the original constants and the trig function. So I'd say it's a win. I think it's a very interesting integral in the sense that it looks challenging until you complete the square in the denominator, and then it just kind of falls apart. That was the only tricky thing I did here. The only trick was to consider this here, x plus r cosine lambda squared. Everything was pretty straightforward from there. And if you enjoyed this, want to see some more, please subscribe, tell your friends. We'll see you next time.